Okay, here's the final video on the 0% to 100% PWM controller that I've introduced in about 2 or 3 videos in the past. So this will be the final video, which I'll describe quickly how the triangle wave that we generated on a previous video on the oscillator design, how that's converted to a square wave, and how that triangle wave is used to modulate the width of the square wave, which basically controls the PWM duty cycle. So if we go back to the circuit here, so if you remember from previous video, we used a current source to feed into a capacitor, whereby we generated a sawtooth wave or a triangular wave, which it basically oscillated between 0.8 volts to 2.5 volts at a frequency of 10 kilohertz. So what we do is, once we do that, we are going to introduce a specific DC offset to control the duty cycle of the square wave. So how do we do that? So basically what we do is we high pass filter the generated triangle wave, because the triangle wave has a DC offset of about 0.8 volts. So if you remember, we had a triangular waveform that was oscillating between 0.8 volts to about 2.5 volts, right? That's what we had, right? And then it kept repeating, right? So now we don't want these DC offset that the switch can only discharge the capacitor to 2.8 volts. That is the VB of this transistor, the turn on voltage, plus the saturation voltage of this transistor. So now what we don't want this DC offset. All we care about is we want the sawtooth waveform. So how do we do that? We just basically high pass filter it or AC couple it to the next stage. The next stage creates a bias that is basically created by the 1K resistors, the two 1K resistors, and a 10K pot. So this 10K pot, it's going to control the duty cycle as it traverses from minimum resistance to maximum resistance. And we take the middle, basically the wiper of the potentiometer, and we basically put it at the end of this capacitor here. What that does is the AC coupled signal, which is the sawtooth waveform or the triangular waveform, will have a determined DC offset that is basically controlled by this pot. As it goes to its maximum resistance, it will introduce a maximum voltage of a maximum DC offset, and as it traverses to its minimum resistance, it will introduce a minimum offset. So if we look at the waveform at this junction here, so if I bring you, as you remember, this is the full circuit. So right now we're looking at the generated triangular waveform now, and in this case I have 25 kilohertz, but that's just because I'm using a smaller capacitance here, about 10 nanofarads, so that shouldn't concern us too much. So basically what we do is we take this waveform basically, and if I look at this point here, so right at this point here, which is found right here, basically it's this point here. This is the 1 nanofarad capacitor that is AC coupling the generated triangular waveform to the next stage. And we see basically you can see that this waveform is riding below and above the 0 point, so that means it's AC coupled. So if I move the ground up slightly, you can see there, right? You can see that it is basically has a specific DC offset. Now, if I control my duty cycle control pot, which gives it a specific DC offset, take a look what happens. So basically, this is the one that controls the duty cycle, which introduces the DC offset. So now if I vary it, you can see right now if you look at, this is where the ground is. Right now there's a specific DC offset that's being introduced into the triangular waveform. Now I could, as it goes to a maximum DC offset, right, sorry, to maximum duty cycle, and as it goes below, as I vary to minimum resistance, you can see that this waveform goes down, right? This waveform goes down, right? And now this is a minimum resistance, right? So that's how we control the duty cycle. Basically, AC couple the generated triangular waveform, and based on this bias of these resistors, we introduce a specific DC offset. That DC offset is coupled into an emitter follower circuit so that it can drive this main switching transistor. So now this is just acting up as a emitter follower, as a buffer, because I don't want to directly try to control this switching transistor, because there isn't enough drive, right? So this emitter follower give me enough drive to do that. Now if you look at the waveform at this location here, is just basically, it would be that waveform minus VB of this transistor. And basically, since this transistor is also turning on and off, there will be the waveform is not going to look exactly like that. So if you look at that, so if you look at this specific location here, that will be at this location here. And that's what it looks like, right? You can see it right now. We're at a minimum duty cycle, right? We just only, now look, I'm gonna move the ground for channel 2 and then increase its magnitude, or its voltage per division. Now if I increase it, look how many, we're at 200 millivolts per division. So 1, 2, 3, 4. So we're about 800 millivolts per division, right? So is the peak where this is 200, right? 1, 2, 3, 4, right? So the peak of this goes to about 0.8 volts, right? Now that 0.8 volts is right here. It will go through this 1K resistor, gets converted into a current, and basically controls this switching transistor. Now take a look what happens now as I vary the duty cycle, right? Just adjust my triggering here. Actually, I'm going to trigger on the square wave for now. Alright, give me cleaner triggering. You can see, right, the magnitude of basically the magnitude of the odd DC offset on the triangular waveform will cause this transistor to turn on more, right? To turn on more as the DC offset is introduced into the triangular waveform that's oscillating at this point. And that's what it looks like, right? Right, and then we just lower the magnitude. You can see 100 duty cycle, right? Let's just do that slightly lower. Yeah, right there. That's how much we have. So 1, 2, 3, 4, right? So you can see the width. That's the width of the DC offset that's controlling the duty cycle. Okay, so now basically this transistor is turning on and off. If we look at the collector side of this transistor, we'll just basically see the 12 volts that comes through here. It will look at a nice square wave that's turning on and off, right? And that's what this upper waveform is basically. So I just wanted to make a quick video trying to kind of close out how this circuit works. and basically kind of describe it fully how it works. Now in this case, I'm not using a motor right now. I'm using a 10 ohm resistor, right? So if you take a look at this, the 10 ohm power resistor that is fed from the 12 volts, right? Now this is the average voltage that's coming out of it as the duty cycle is controlled. Look at the average voltage that's across it. So if we look at maximum duty cycle, right? Maximum duty cycle, 100%, we get almost 11 volts. And if we lower the duty cycle, the average voltage goes down, right? Just right, 10%, right? 10% of 11 volts is 1.1 volts, right? 1.1 volt, right? That's what that is, right? So yeah, so now how do you use this in a closed loop circuit? Now someone asked in the previous video that this is not closed loop control, right? Yes, of course it's not. So what you do is, in case of for example, a motor that you want to control the speed, what you do is you convert the speed into a voltage that could be fed back into the circuit here. So how do we do that? For example, for a brush DC motor, you can basically measure its speed. The speed is proportional to the EMF that's generated across this. You can use that, or you can use an optocoupler that measures the rotational, right? The rotational frequency of this motor, and that could be converted to a square wave. The square wave has a specific frequency. That frequency can be converted, can be low pass filtered and create an average voltage. That average voltage can be fed back into here and be summated into the voltage that's being included in, that's generating the offset here in a negative feedback fashion to generate, as the frequency goes up, right, the average voltage will go up, and then that average voltage will be subtracted from this voltage that's going into the it's generated, that's being offsetted into this circuit here, and that will lower the duty cycle, right? Or as the frequency goes down, the average voltage will go down as well. Now that gets inverted and will generate a higher DC offset in here, and that higher DC offset will generate a higher duty cycle, thereby maintaining a specific speed in this motor. That's one application you can use. There's a lot of other applications that you can use this in a closed loop environment, as long as you can generate, when you're controlling a proportional voltage that varies with that quantity that you're controlling. You can feed it back into here. You can add it into this node here, right? You can add it into this node either using an op amp, or just or basically some sort of a difference amplifier, and that would create the error signal that would control the duty cycle, basically, right? So that's how you can use this circuit. So this will be the last video in this circuit. I hope you'll find it useful, and basically you can use it in a lot of applications. It's a very useful circuit, right? So yeah, okay, I hope you enjoyed this video. I'll take a look. We'll meet up in another video where we'll get an application on another circuit that helps us to perform useful tasks. All right, take care. Bye-bye.